Section 1.5, our objective today is to apply postulates and theorems that refer to points. Today we are actually starting looking at the first of our theorems, but in order to do that we need to remember a couple things. Remember that a postulate or an axiom is a statement accepted without proof. So in other words, we just accept it. It is true, and we just go on from there. We can use it, apply it, and it's true, okay? A theorem, however, are important statements that must be proved. Now, in a theorem is made up of two parts. The first part is called the hypothesis, and that is the condition required. So it's if you have this certain condition. And then the second part is the conclusion. So if you have this certain condition, then you are guaranteed a certain result when the condition is met. Okay? So we are going to learn today our first postulates and theorems, and I want to let you know that even though I've included numbers here, I do not want you to memorize the numbers. I want you to memorize what they say. Okay? So the first postulate, it says a line contains at least 2 points. So any line, on any line, you can locate at least 2 points. That's what the postulate is saying. So on this line, I can locate point A and point B. Okay? So every line gives you at least 2 points. The second statement says a plane contains at least 3 points. And the key here is not all in one line. So when you want to talk about a plane, you have to have at least 3 points, and the 3 points cannot be collinear. That's what not all in one line means. It means that they're not collinear. So in order to determine a plane, you have to have 3 points not on the same line. Yes? Okay, and the third statement says space contains at least 4 points, not all in one plane. So when we're talking about space, which is a three-dimensional idea, okay, so we have to have at least 4 points. So here's point A, B, C, and point D is down here. It's not in the same plane as A, B, and C. So we have to have that situation. Okay? The next postulate says through any 2 points there's exactly one line. Another way to say this is through any 2 points there's one and only one line. So if you have any 2 points, wherever they are, there's only one line that you can draw, one unique line that you can draw that goes through those 2 points. So any 2 points determine a line, is what that's saying. Okay? Postulate number 7, through any 3 points there is at least one plane. Okay, that's the first part of the statement. And through any 3 non-collinear points, that should say 3 here, typing there, there is exactly one plane. So what that's saying is that if you have 3 points, there's at least one plane that goes through it. And actually, there's infinite planes that would go through those 3 points, because the planes could go through at different angles. But through any 3 non-collinear points, you can only have one plane. It's unique. Anytime you have 3 non-collinear points, they represent a unique plane. So if I have this triangle with coordinates, with vertex points A, B, and C, that triangle is also represents a plane, because those 3 points are non-collinear. Okay? If 2 points are in a plane, then the line that contains the points is in that plane, is the next postulate. So that's saying you have some plane, and you have any 2 points in the plane. And a previous postulate said that if you have 2 points, there's a unique line that goes through those 2 points. Well, what this postulate is saying is that every point that belongs to that line also belongs in the plane. So it's a key idea. If 2 points are in a plane, then the line that contains the points is in the plane. So not only are these 2 points in the plane, all the points on the line are in the plane. And the next postulate says, if 2 planes intersect, then their intersection is a line. So, in other words, if you have this plane, and this plane, and they intersect in such a way, and then the points that belong to both planes represent a line. Okay? And I didn't do a very good job drawing that, but if you picture our classroom, these are walls that meet in our classroom, and so this is plane 1, and this is plane 2, and they intersect at this corner. That corner represents a line, so that's probably a better way to see it than my original drawing. Note, exactly one and one and only one have the same meaning, so they're interchangeable. So when we say exactly one, it means one and only one, and in other words, it means they're unique. Okay? They're the only ones that exist. Okay? And then that brings us to our very first theorem. And again, I want to remind you, I do not want you to memorize, theorem 1. I want you to memorize what it says. It says if 2 lines intersect, so this is the condition. If this happens, so if you have that condition, so 2 lines intersect, here's line L, and here's line N. Those are 2 lines that intersect, so this condition is met. Then the conclusion is guaranteed. They intersect in exactly one point. So the one point they intersect in is right here. We're going to call that point X. Okay? So any 2 lines that intersect, they intersect in exactly one point. One and only one point. Okay? Theorem 2. Through a line and a point not in the line, there's exactly one plane. Okay, so here's the situation. I have a line, but to have a line, I have to have at least 2 points. So I have point A and point B. And through a point not on or in the line, so let's put a point C up here. Okay, so that's my condition. Through a line and a point not in the line. Well, what's another way of saying what this picture shows? Points A, B, and C are what kind of points? They are 3 non-collinear points. Well, we have a postulate that says if you have three non-collinear points, then there's one plane. So the theorem says there is exactly one plane. So that's a unique plane that contains all three of those points. Theorem 3 says if two lines intersect, that's the condition, that's what we have to have, then exactly one plane contains the lines. Okay, well, to have exactly one plane, I have to have three non-collinear points. So if two lines intersect, do I have three non-collinear points? Here's line L, but we know from the previous postulate that line L has to have 2 points. And here's line H, and we know from that previous postulate that line H also has to have at least 2 points. So in this picture, are there three non-collinear points? Yes, there are. I could say CDB are three non-collinear points. I could say BAD are three non-collinear points. And so if I have three non-collinear points, then there's exactly one plane. So all of this is in exactly one plane.